Today, sir, will be majorly covering on the topic of quantum information, coherence, and noise, along with the cross operator. If I'm not wrong, sir, please correct me if these are the content of today's topic, might be. So, I'm just handing over the session to Mustafizur, sir, and sir, you can just take over the charge from here.
Yeah, thank you so much, Doctor. Um, Dr. Ashish sir. So it's really an honor. And the last class yesterday we have covered some of the basic knowledge of digital communication technology as a whole, and some aspects of the quantum signal, those things, as well as the classical information, some definitions only, right? So itself, classical information, digital communication, quantum information, quantum communication, these are independent subjects. In fact, there are degree courses on it. Okay, so covering this entire subject is in 1 hour is never a possibility. So I'm trying to give you an overview and sufficient references so that you can revisit the content as per your interest. So let us start. Today, we'll be mostly covering the topic quantum information. And just let me know that you can see my screen, you can listen my voice. Please confirm in the chat box so that I can start. Maybe in the chat box. Yes, thank you so much.
Yes, sir. You are quite audible, and your screen is properly visible from our end.
Thank you so much. Okay, so we'll be covering today, as already Dr. Ashish said, like basic ideas of quantum information, noise, and some introductory ideas of the Krauss operators. So these are actually advanced topics, and please bear with me. I am trying to give as simplified version of the quantum information theory as possible. And if you stuck somewhere, maybe we can interact later on, or there are advanced subject like QT-06 and other subjects where these details will be available. Okay. So these, I'll suggest these two particular books. Those who do not have the basic information theory background, so they can consult with the book two. And for the specific for the topic today, quantum information theory. So we'll be referring the book one, Quantum Information Theory by Mark Wild. And let's start. So already, because you already have covered, most of you, the QT-01 subject and much portion of the QT-02. So you often has come across with the definition that is some wave function that is encoded as a quantum state is denoted by some alpha ket 0 plus beta ket 1, right? And as I told yesterday, that these are typically column vectors, right? Typically column vectors with certain properties, right? So the first property, so these all the details again will be reused today. So that they are actually the if you take the inner product with itself, or if you do the like probability sum square, you should get ideally t is equals to 1. And they basically all these amplitudes alpha beta, they are some complex numbers, right? As well as the sum of the complex numbers, square of them, that is these are probabilities, right? Probabilities. So probabilities of getting the state at ket 0 is alpha square, and probability of getting the state in ket 1 is beta squared. So this should be equals to 1. In general, you can represent any quantum state with arbitrary amplitude, some amplitude alpha I, and if the basis is ket I for all I, right? So I was trying to relate this to the signal processing part yesterday, and just note that uh, this is let us just look at from the mathematical perspective or the linear algebraic way that any signal xt, right, any time domain signal. So this is something. So if you take a discrete realization of this is nothing but your time step at t equals to 0, at t equals to 1, at t equals to 2, and so on, right? Similarly, this particular signal, what Fourier series says, like considering the periodicity definitely, but you can remove the condition of periodicity for Fourier transform as well. The same signal, if you consider them as a vector, you can represent them with some coefficients beta with the Fourier basis vector. Say for example, Fourier basis vector are your f vector. Okay, fi for all I. So this is your Fourier series representation or Fourier transform representations, right? For so any coefficient times the Fourier coefficient. Similarly, the same vector you can also represent in the eigenbasis, that some coefficient say alpha I prime and your eigenbasis ei, right? Similarly, you can also denote your quantum signal kx as a probability amplitude times the basis vector kit I. Here I is the computational basis for all I. These are actually computational basis. And by computational basis, I mean kit 0 or kit 00 for 2 qubit, or it may be kit 000 for 3 qubit and so on. So it can be something like alpha 1 0 1, alpha 0 0 0 plus alpha 2 0 1 0, and so on up to alpha 7 um, 1 1 1 is a 8 bit representation of your signal kx, right? So this is the way how we represent signal or the quantum state on a quantum computer. So there is a lot of theories already covered, and yesterday we have defined a new term for noisy case or some ensembles case. So that is density matrix definition. So I do not have any slides today. I'll cover everything, just a pen paper. That is I mean, the method I like most. Okay. So yesterday we defined something. Now instead of giving a definition, I already have shared some notes with Professor Pilli sir, and he will be sharing with you. But I'm not going to the notes or definition, just with intuitive and mathematical way of understanding the subject. So we know that psi is, say, let us take some psi, okay? Um, so psi, let's take, we start with a kit 0 state, okay? And we apply a Hadamard gate, right? So what we'll be getting? So definition of Hadamard gate is what? Definition of Hadamard gate is 1 upon square root 2, 1, 1, 1, and minus 1, right? And if you apply the Hadamard gate on the quantum state 0, what you get? H times this kit state 0. That means a matrix times a vector, that is H into kit, just let me take the eraser maybe. Yeah. So H times kit 0 is your square root 2 and 1, 1, 1 minus 1 times your kit 0 state is 1, 0, right? And if you simply multiply it, just forget about this 1 by square root 2 part. If you just simply do the multiplication of this, you'll get some state that is kit 1 plus kit 0, okay? And the normalization factor 1 by square root 2, this part, right? Just simply, so basically if you multiply this, you'll be getting something like this 1 1, right? And 1 1, you actually can do something like this 1 0 plus 0 1, right? So 1 0 is basically your kit 0 state, and this is basically your kit 1 state. So simple multiplication. So this is a state, and that particular state we called a superposition state, right? Superposition state. And this particular gate we called as Hadamard gate. Hadamard gate. And suppose this state normally physicists also denote as plus gate. this H times 0, that is superposition gate. The actual state is this is equals to 1 by square root 2 gate 0 plus gate 1. Okay. And this is the state. Suppose we start with this plus state, superposition state. Okay. This is our initial point, suppose. Okay. Now, yesterday we have certain things. So suppose let's do the density matrix rho, which is the outer product of psi and psi. Okay. So what happens? We have defined psi as plus state, outer product of plus state, right? And your plus state is actually outer product means just kit psi is nothing but some matrix, okay, column matrix. So if you feel uncomfortable with this notation psi, just take some x, take some x. So basically this is nothing but if x star is the column vector and x is the row vector, right? So this is equivalent to x star of star and x star, that is x star, right? This is simple algebra, right? And this is basically outer product. So I am assuming some of the scholars, some of the students might lack the algebra background and probability background. So I'll touch a little bit on that part, how these things are related. So this is same as this. This notation is the Dirac notation, to appreciate the scientist Dirac who discovered this kind of notation. And this is simple algebraic notation. Simple algebraic notation. Similarly, if you have inner product, so inner product is simply x star x, okay, and the Dirac notation is x x, okay, same thing. Now let's define a density matrix which is an outer product of the states psi and psi, and then basically you will find that this is actually so the first state, the plus state is what, 1 upon square root 2 kate 0 plus kate 1, right? So this vector, right, plus, and you are doing on top of it something like this, kate 0 plus kate 1 as outer product. So I'm putting star here, right? So this is same as the outer product, this notation. So this is the Dirac notation, and this is the simple algebraic notations. So what is happening? So this is a column vector, this is a column vector, and together it's becoming a row vector. A column vector time a row vector is a outer product, right? It's a matrix, and you will see that you are getting so basically 1 upon square root in front of this and 1 upon square root in front of this. So together multiplication factor will become 1 upon 2. And if you simply multiply all these things and sum up by simply taking kate 0 equals to 1 0 and kate 1 equals to 0 1, right? Okay, just let me know what is this matrix. I'm giving you 1 minute, so I'll see the answer in the chat box. Okay, so I need 100% concentration, so sometimes I give some questions to solve. Let's just simply put these vectors 1 0 plus 0 1, and just forget about these coefficients. So because these coefficient and these coefficients are taken care here. Okay, just simply multiply these two vectors and let me know what is the answer here. Correct. So the answer is 1 1 1 1. So this is the density matrix for your superposition state, half of 1 1 1 1. So same thing. This is equivalent to the state plus. This is the vector notation, and this is the matrix notation, right? Okay, these are equivalent. So the thing is same. Now let's discuss a little bit more. So actually, the objective of the density matrix is more than this. So the thing what we studied yesterday is that you might have some impurity in the state generation or noise or decoherence or something like that, which is actually your state should be psi, but what you are getting some psi I. Means there are for several I equals to say you are taking suppose 1, 2, 3 and so on. For different instance, you are getting psi 1, psi 2, psi 3 and so on. Many such possibilities. So this is called ensemble of states or ensembles. Now every such state, because they are randomly coming as an event, right? So this is like generation of qubit or the qubit that you are preparing in a physical system. That is a random event. And all these quantities we are calling as random variable, right? And then basically each random variable might have an associated probability P1, P2 up to Pn, right? So these are the probability of the occurrence of each individual state. Then we can define these ensembles in a better way, that Pi psi I, right? This is the way how we can, that each state psi 1 has an associated probability P1, right? So then basically, if all the states are equally likely, that you that means the probability distribution is something like this. So any instant you will get the same probability. So if this is your probability and this is Pi versus I plot. So any instant you do the experiment, then you are getting the same result. That means all the quantum states are equal probable, right? Then you will have only the same thing psi I, psi 1, psi 2, psi 3 with all the same probability, like 1 by the number of trials, right? So another definition of rho, that is a generalized definition. So that is basically sum over I, associated probability Pi, and the outer product psi I and psi I. Now, if all are equal probable, that this probability is equal for all, then if equally likely, okay, then basically what you are getting, you'll be getting this is as rho equals to simply the outer product of your psi and psi, right? Because this is 1 by, so Pi will be some 1 by n, right? 1 upon n, because the probability will be the 1 by number of trial. And then the sum will give you, sum over I will give you another n, right? N times the outer product psi I and psi I. This n and n will cancel out. So ultimately you'll be getting psi times psi, right? So this is called a pure state. This is called a pure state. And for impure state or mixed state, impure state, this probability can be anything, like Pi can be anything. Can be anything. Okay. Now there are several things will come. What are the things? What are the properties and all? So before that, so let me define a state. So probably this state is already covered with you, entangled state or entanglement, and you already have taught the Bell state, right? So what was the Bell state? You already have started with the initial state QT-0, and you take another state QT-0. First state, you create a superposition. So what is the output of the superposition? You get a plus state, right? And then in the second qubit, between first qubit and second qubit, you put an entangle gate, say some Cnot, okay? And then you do some measurement, okay? So before the measurement, what is your this particular state, right? So let's evolve. Let's understand this circuit. So first of all, you started. Suppose this is your step 0, and suppose this is your step 1, and this is your step 2. So step 0 is basically you started with 0 and 0. That means your state is 0 tensor product with 0, right? So this is how we represent the circuit. And step 1, what you have done, you have applied the Hadamard on the first qubit, but the second qubit you have done nothing, right? So what effectively you have done is first qubit will be 0 plus gate 1, and second qubit will be intact gate 0, right? And then basically there is some coefficient 1 by square root 2. Okay. Now what is your step 2? Step 2, you are applying CX gate or the Cnot gate, right? And the definition of Cnot, if you see, so it is something like this: outer product with 0, 0, tensor product identity, plus outer product 1, 1, and tensor product with X. What does this mean? What does this mean? It means that if you apply a CX gate on top of this state, like here, so when it is so first let us write the final state for this. So 1 upon square root 2 is fine. So what you are getting? You are getting 0, 0 state plus 1, 0 state, right? This is your state here. So let me take a separate color. Maybe this is the state you are getting in this stage. Okay. Now here we'll be checking. This is our step 2. So what we are getting is this particular definition tells us that if the first qubit is 0, this gate will do nothing. If the first qubit is 1, it will do bit flip on the second particular qubit. Okay. And what is bit flip? Whether it's a quantum gate or not, it's a noisy gate or not, will come. Why I'm covering this part in quantum information side. So what I'm telling, if the first qubit is 0, it will do nothing on the second qubit. If the first qubit is 1, then only it do the phase flip, bit flip on the second qubit. That's why it is called controlled NOT gate. Controlled NOT gate. Now our state will become, here our state will be 1 upon square root 2, and first state will be intact 0, 0, second state will become 1. So this particular state, the implication is that if you measure the first qubit, you definitely know that the next qubit is also in state 0. If you measure the first qubit as 1, you are 100% sure about that the second qubit is again 1. So this is called an entangled state. Sometimes it is written as high plus state. Okay. And this is the Bell circuit. Now the question is, let us understand the Bell circuit from the classical information theory side, right? So if two states are highly entangled, highly correlated, like a Bell state, and you are measuring a state 0, what is the information about the second qubit? So if it is an entangled state, you are definitely sure that next qubit is 0. There is no intermediate state 0, 1 or 1, 0. Okay. These two states are not valid, right? Only possibility is 0, 0 and 1, 1, and you are only measuring 0. That means the next qubit has to be 0. That means there is no classical information as such. You are very much sure about some event, so there is no as such classical information. But this state has many things to do in quantum computing. Okay, so this is the motivation for today's class. Now, so any question till now, like till this point, how the Bell circuit works or anything like? I think okay, fine. Okay, now let's talk more about the mixed state. I already can you please repeat the C0 gate? Yeah, sure. C0 gate. C in the book you have seen it is written like this, right? 1 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0. This is the definition of Cnot gate, right? And you see, so the position of these two one, okay? So what is actually you are doing if you think as a bipartite system or a two-level system, this is same as outer product of 0, 0. So outer product of 0, 0 will be what? 0, 0 means what? 0 means your only it is 1, 0. It's a 2 cross 1 vector. So together it's a 2 cross 2, right? 2 cross 2 matrix. Tensor product with some identity matrix. So it's becoming a 4 cross 4 matrix now because you're doing a tensor product with another 2 cross 2. So it will effectively become 4 cross 4 matrix, this part, 4 cross 4 matrix plus kit kit 1 outer product with kit 1 tensor product with kit the Pauli X gate. This is Pauli X gate, okay? Pauli X gate, right? So look at this equation. So I am explaining in a way, this is not the correct way that I should explain. So you look, this is similarly as identity, right? And this is your X gate. This is just for remembering why the definition is just such. So you are creating a 4 cross 4 dimensional space where on the first 2 cross 2 positional, the way that it works on the 0. So what I said is if the first qubit is 0, so it will do nothing on the second qubit. Okay. So this is equivalent to this particular representation in the 4 cross 4 dimensional space. And if the first qubit is 1, then whatever be here, it will do a bit flip here. Bit flip here. If it is 1, 0, it will become 1, 1. If it is 1, 1, it will become 1, 0. So this is the purpose of X gate. X gate in 2 qubit circuit. So X gate normally work on 1 qubit. That's why it's a CX gate. Okay. And control CX gate. And the entire definition is this. This is another 4 cross 4. And if you divide the 4 cross 4 matrix into submatrices, right? So in the first submatrix 1, 0, 0, 1, this is identity matrix. And in the fourth place, like fourth quadrant, it is 0, 1, 1, 0, it's X gate. So the definition is 0, 0 tensor product I and 1, 1 tensor product X. I hope it's clear, right? Okay, is applying Hadamard to the first qubit and then Cnot to the second qubit is the only combination of gates that result Bell state? No. There are 4 different combinations of Bell state. I'm not going detail because somebody will tell in quantum computing class I should not cover these aspects, but there are other possibilities. Yeah. Got it, said the way explanation is best to understand perfectly for looking like yes. Oh, thank you so much. Okay, let's look at some other things, mixed gate and all. So quantum information theory, there are a lot of things. I'm just covering some of the basic aspects. Maybe some of you might be interested in future to work on quantum noise and other related subjects. I hope there will be some subjects like quantum communication, quantum signal processing, much good safe in future. Right now, it's in very nascent stage, in baby stage. So things are not much defined properly. So I'm trying to give some flavor of it, but this kind of initial understanding might help the demonstration of future subjects. So, okay. So a mixed state, the mixed state we defined something like this, rho equals to for many such possibilities, many instant I, it is the probability and the outer product psi and psi. And there is a mixture of the probability. That means they might not be equal probable. Okay. Now, let me quickly give you one question from this definition. Quick question. Suppose we have a Ket 0 state with probability equals to half, and we have another state Ket 1 with probability half. Okay. Then somebody let me know what is rho mixed state. Okay. So, okay, let me see who gives the first answer. Just understanding of probability is sufficient to define this. I already have give the definition. I put the mixture. So you are creating some quantum state where the generation of, like in normal digital communication, you create lots of zeros, lots of one bit string, right? Symbols, okay, to transmit your data. So what is the probability of transmitting lots of zeros? Suppose it is here half, and the probability of transmitting lots of one is probability again half. That means there is unbiased, like they are equally likely of generation of probability. What is rho? Uh, Yes, yes. So one is not the correct answer. It is the outer product. So it will be some matrix. So let me know the element of the matrix. Even if you do not give me the fraction part, that's okay. But just the structure of the matrix is important. How it looks like. It should be something like this. Hope. Yes, yes, correct. Thank you. Okay, now there are more thing about rho. Rho is just not a rho in this particular subject. So properties, and these properties are extremely important. First of all, the this matrix rho is um, rho dagger rho equals to rho dagger equals to that. That means it's a Hermitian matrix. Hermitian matrix. So basically, rho can be some real matrix Rn cross n, or rho can be any complex matrix n cross n. But in general, so normally we write rho transpose equals to rho for real and rho star equals to rho for complex, but together normally write as rho dagger equals to rho. Okay, so general rotation for transposition. So in general, if it is complex, we need to do transpose as well as the complex conjugation by definition. Okay. So this is the first property. Then the next property, which is important one, is trace of the matrix rho equals to 1. So because you are dealing with probability, right? So our definition was what? Our definition was this one. This was our definition, right? So if this is our definition, so then basically you will see. So if there are mixture of probabilities of states, and we are taking the product of individual states, outer product of the individual states, then it has some associated probability. But what is the sum of all probability of all states? So that should be equals to 1. Okay. So trace of and why I'm taking the trace of rho. Okay, I'll come. This is basically related to the algebra. We'll prove it. Okay, later. So trace of the matrix rho equals to 1. Second, third property is this is a positive semi-definite matrix, PSD matrix. This is a PSD matrix, positive semi-definite matrix. That means if you have any vector phi, any vector phi or x, y, z, whatever it is, we have phi rho phi. This particular inner product, like this particular product phi times the matrix rho times the vector, the row vector phi. This entire thing will give us one scalar quantity. Okay, this should be greater equals to 0. This is the PSD matrix. So there are other interpretations as well, like trace of rho square for pure state. The trace of so pure state. If it is a pure state, then trace of rho square equals to 1. And for mixed state, yes, trace of rho is the same as the sum of diagonal matrix, correct? And so, okay, and if it is a mixed state, then trace of rho square may be less than 1. It can be less than 1, right? So let us prove this first. So I won't go the rigorous mathematical proof, but better let us take an example and prove it. Okay. Suppose let's take some quantum state psi as your alpha and beta. Okay. These are the probability amplitudes. Okay, alpha and beta. So what is the outer product of this state? Outer product of your psi and psi. So let's take alpha beta some real numbers for simplicity. So it is alpha square beta square. This is alpha beta, and this is also alpha beta or beta alpha, whatever you write the way, because they are simply real numbers. So same thing. So alpha square alpha beta beta square is your outer product state, right? And we know that psi, when we represent it, is alpha times state 0 plus beta times state 1, where these alpha and betas are the probabilities. So this is the this is the first level of probabilities, right? Alpha square and beta square are the probabilities. This is the first level of probabilities defined in a quantum state. But there is a second level of probability defined here. You see this particular pi. So already each psi contains some probability. The probability are the probability for computational basis states, that is basically generating the psi. That means psi equals to some alpha 0 plus beta 1, this probability. And because all these psi, they themselves has the uncertainty. So another level of probability is coming here from the density matrix definition. Two different probabilities are coming into picture here. We need to notice. Okay. So that's why I said yesterday that quantum information is more than the probability. Okay. So now you see that even just by doing the outer product of simple one single state, same state, okay, psi and psi, alpha square, alpha beta, and beta square, where these individual terms are some probabilities, right? Now, if you do the outer product of 0 and 0 for simplicity, right? Outer product of 0 and 0. So what is your so from here let us do, okay. So what is the trace of this matrix? Suppose this particular outer product, let us call as a hat as a matrix, okay. So what is the trace of a hat? Trace of a hat is alpha square plus beta square, right? And we already know if it is a pure state, psi is a pure state, then we also know that sum of the probability is alpha square and beta square. Just check these two equations, they are same in fact, right? Alpha square and beta square, right? But if you take a mixture of such states, so then this position will not belong just simply alpha square and beta square. There may be other terms and all. Then you will see for mixed state, you are getting more number of terms. Okay. And I mean, we can prove it with some examples that this is no longer equals to 1. No longer equals to 1 for the impure state. So for the pure state, this is already confirmed from the definition. So you can, for simple proof, you can take a QT-0 state. So this is basically 1 0 outer product with 1 0, and the resultant will be 1 0 0 0. And if you take the trace of this matrix, you'll be getting 1, right? But now you take some state, some impure state, you do 0 0. So let's prove it with another example. So suppose our state is 0 0 plus 1 1. This is our state, right? So this state is what? This state is 1 0 0 0. And this state is what? This state may be something else, like, for example, this can be your, maybe this is correct or wrong, I don't know, I need to check. But you'll see that trace is here equals to 2, right? But again, like the trace equals to 2, but this is not a impure state. Like together you can represent them as a single state psi, but I am assuming this is one state psi 1 and this is another state psi 2 here, okay. And this may not be the trace equals to 1, right? But if you normalize here again with by 1 by half, you'll see it can be a pure state, like trace equals to 1. So this kind of experiments you can check whether this is correct or not. So let's do more on the mixed state, and that is called the expectation of mixed state. So suppose suppose we have some state rho. Suppose we have some state rho. Okay. Okay. Although rho is some matrix, but some books they prefer to write as Kate rho, like a quantum state. So in general, we prefer this Kate notation for vectors, but in some books you will see rho matrix is also denoted like this, but that's okay. Like whether you do it or not, that's okay, right? So suppose rho is defined in this way, half of. Okay, so you wrote a square on the row in the previous slide, that is computing the row square, right? Okay, let me check this one, right? Yes, so computing the row square, right? So yes, typically you can do like that. Then basically you have to multiply two matrices, right? Yeah, that is the thing. Okay, I just showed the example for one matrix, but you can do with a square by definition. You are correct, actually. Thank you for suggesting it. Yeah, I mean, whatever result we have got, like it will be something else by doing the square that we need to consider. I just took some random example. Okay, thank you. Okay, so now if there is a time evolution, right? So in general, time evolution part I'll come later, just for the timing. Okay, take some density matrix or the state as half of some y1 as your first quantum state outer product with y1 plus half of y2 and y2. Suppose this is our quantum state right now. Yes, correct. So rho squared equals to rho for the pure state. Yeah, I mean there are properties, at least 7 to 8 properties. I just gave some properties, and like I shared the note. There are more like properties are there. Yeah. So I'm following the chat. So yeah. So okay. So now let us define this part as rho 1 and let us define this part as rho 2. Okay, two density matrices. As the that means the total density matrix. Suppose these are sum of two density matrix, rho 1 and rho 2. Okay. And suppose there is some observable O hat, it is some matrix. Okay, some matrix. I'm just removing the physics part of it, just some matrix. I mean, it has some special properties. I'm just not covering it today. Okay, so the expectation of an operator. So normally, given the quantum state y1 is, so that is the expectation corresponding to the quantum state y1. This particular thing of this operator O1, that is the expectation operator. That is y1 O had y1, and this is equals to trace of rho 1 O had. So this is one property. Okay, so property for the mixed state while computing the expectation of a particular operator, and many of you might be facing difficulty here. Okay, I'll solve this difficulty. Just allow me for 5 minutes. Okay, so this is one, and for the part y2. Okay, y2 is another quantum state. For that, suppose the expectation of the operator O had sorry. We take the relation, and it is y2 outer product like the O had y2, the whole expectation value, that is equals to trace rho 2 O hat. Why I'm writing the trace with the expectation? What is the relation? I'll come. So these are the two things. Then by the classical probability law, because these are the expectation values, then the overall expectation will be half of the sum of expectation of O1 plus half of the sum of expectation of O2. There is a detailed proof in my notes which I shared, and you will see this is equals to trace of your rho O hat. Okay. Now the question is how this relation, why I'm taking this particular property. So let us prove it from linear algebra. So so suppose there is an operator A. Okay. So what an operator does? Suppose you have some vector x, and if you apply an operator A, okay, so A times x, and this is related with the eigen equation Ax equals to lambda x. We all know this particular equation. So if we can find some x which is not equals to 0, some non-zero vector, such that A times x equals to lambda x, this is what we call the eigenvalue equation. I believe this is the most important equation in all science and engineering. Eigenvalue equation. Now you see, in physics, physicists call this an operator if given x is some wave function, and if I apply some operator A on the wave function x, then if I measure after whatever I need to do, whatever I get, the eigenvalue is the desired quantity. Desired quantity. So if my desired quantity has to be real, then A has to be Hermitian. That means A dagger equals to A. This is by simple mathematics. Like if a matrix is Hermitian, all its eigenvalues are real. That means what? So if there is a momentum operator P hat, and I apply to a wave function psi, I should get back the momentum value, momentum quantity, right? Here, momentum quantity here, P times the wave function, right? So say for example, if I have an Hamiltonian as an operator, if I apply to the wave function, I should get energy value back, because Hamiltonian operator gives the energy, and this energy is the eigenvalues, right? So that's why these particular matrices, or they may have differential form as well, are called the operators. And many times we are interested to know the expectation value of an operator A. Okay, this computation is one of the extremely important computation in physics and computing, for those who are interested to find the ground state energy of some hydrogen molecule or methane or benzene or whatever it is, like some drugs. Okay, you want to design certain drugs, so you need to understand what is the energies of its chemical or orbital configurations, right? So this expectation calculation is extremely important. So today I may not get time how the expectation is computed on a quantum computer, because it's information theory class, but maybe some future class I'll show what is the quantum circuit to do this. Okay, so for now, this is for the wave function, say x, I mean for some simple vector x a x. Okay, this is the expectation for a given vector x. Okay, for given some x. In physics it may be some psi. Okay, in normal engineering it can be some x. Okay, now our claim is that a equals to x, a x equals to trace of rho A. This is our claim, where we defined rho as outer product of x and x. So those who already knows bit of mathematics, this is trivial for you, but I felt that this might be difficult for some of the students, so I'm covering this proof. Okay. So So kx is what? Kx is basically your x star, right? It's some vector. Okay, some column vector. Some column vector. Okay. For x bar some row vector. So row vector in quantum computing represented like bra notation. Sorry. So just some this notation x bra, right? So let's take x is some unknown state, that is alpha and beta, this thing. So like alpha times get 0 and beta times 1, same thing. And suppose define a row is x and x, and you'll be getting them as like alpha beta column vector times the row vector alpha beta. And what you'll be getting alpha square, suppose they are real numbers, alpha beta, beta alpha, beta square, right? So and now take some operator a, sum a, and let's define a as okay, physicists will take a1, a2, a2, a3, but you as an engineer you can take something else. Okay, a1, a2, a3 and a4. Okay, maybe, I mean, if they are like symmetric matrix like a star also, you can take something like that, or just simply just remove this condition as an engineer, just take this one, just simple some ordinary a. Okay, now let us do rho times a. So rho times a is what? Rho times a is alpha square, alpha beta, beta alpha, beta square. This was our rho times the a1, a2, a3 and a4, 4 elements of a matrix A. Now if you multiply these things, I won't multiply each and every term, but I'll only find this point and this point, because this will help us to calculate the trace, right? Because we are interested to compute the trace of this thing, right? So the first part will be what? The first part will be a1 alpha square plus, I may be wrong, okay, please correct me if I am wrong. So so a1 alpha square, right, plus then this multiplied with this, so a3 alpha beta. So these are the terms. Then here the terms will be I need to consider this and this. So it will be your a2 beta alpha, right, plus a4 beta square, right? So our result is so just our result will be a1 alpha square plus a3, sorry, just doing the wrong thing again and again. Then so a3 alpha beta plus a2 beta alpha plus a4 beta square. Suppose this is our result 1. Okay, and let's do this particular thing, x ax. You see, there is no row here, right? Simple x, a and x. Okay, so x is what? X is your this is bra x, right? This part is bra x, so alpha and beta row vector, right? And then there is a matrix, and the matrix is a1, a2, a3, a4, and then there is a column vector alpha, beta. Fine. So just simply multiply these things. So the first part, let's keep it intact and just first multiply these two part. Okay, so what you'll be getting, so it's a 2 cross 2 matrix, it's a 2 cross 1 vector, so effectively you'll be getting something like 2 cross 1. So let's do it. It will be a1 times alpha plus a2 times beta, right? I'm writing outside, so pardon me. And then the next part will be a3 alpha plus a4 beta. Now if you multiply these two, so this is a particularly 1 cross 2, so it will be a 1 cross 1 scalar quantity, and you see it is 1 times alpha square plus a2 times alpha beta plus a3 times alpha beta plus A4 times beta square, and this is our result 2. Now, let us compare the previous result. So this was our result 1 by doing the trace of two matrices, right? Rho and A, right? So what we have done? What is rho? Trace of the property, trace of, okay, let's take the A left side, like trace of AB equals to trace of BA. This is the property of trace. So what we can do, trace of A times rho, that is basically trace of A times an outer product of two state. This is, we are proving the trace of the outer product of two states times a matrix is same as the inner product. So x is what? It is inner product, right? So forget about A. This is inner product, right? So inner product of two vectors is same as the trace of the outer product. So this is the property we are proving here. So you see result 2 is same as the result 1, right? Any question here till now? So why I'm doing this? Because when you will be trying to design some quantum circuit for this, sometimes you will prefer that this circuit is good for you. Sometimes you'll see that you can find a better circuit for this. So that's why this property is important for you. So mathematically, this is fine. This is good for understanding each and individual element of the matrices. But implementation wise, expectation calculation with the inner product circuit is more less complex in terms of the quantum gates and all. Here you see you are operating on two matrices, rho and O, rho and A. Suppose rho is n cross n matrix and A is another n cross n matrix. So if you design a circuit on this, so the complexity is two matrix multiplication, right? It's huge, right? But here you are only doing a matrix times vectors or a vector times a matrix, right? So it's a less complex, like n cross 1 times n cross n. Now mathematically it's the same thing, but when you actually try to design the circuits, probably you will be finding a better way to solve this problem. Okay, so these are the complexity theoretic understanding of the inner product and outer product, although they are mathematically the same thing. So let me know if you have any problem till now. Like you can put in the chat box, and also let me know, like if you feel so boring, I won't, like I go in a different way then. Yes, trace is related to the inner product, exactly. That is what I just have given a proof, and I'll give an alternate proof also. This is just I have done the way it works with simple example, but I'll give you a trick wise solution as well. What is the off diagonal element in row matrix correspond to? What is the off diagonal element in row matrix correspond to? Off diagonal so you are calculating the, okay, what is the off diagonal element? Oh, off diagonal element I am not calculating, because to calculate the trace you just need the diagonal elements. Shouldn't the probability be considered while calculating row? Yes. So all these alpha, beta are the probability amplitudes. And I just have given you the calculation for the pure state, definitely, like some density matrix with simple x and x. But if you take the impure state, like you have some state, suppose you take some rho equals to, now suppose your rho is a complicated one, x and x with probability p1, right? Plus probability p2 and another state y and y. Definitely you can prove the same theorem, but with more calculations, right? So this is an impure state. The proof I have given for the pure state, but the property again holds true for this impure state as well. Okay. Normally, when I take class for purely like this semester, I was taking class for the student at Asian Bose, and they are people from mostly condensed matter physics. So yeah, I mean, I tried sometime uh, like relate the quantum information theoretic part with the quantum computing part, but in general, it's difficult to always correlate. Okay, so now give a trick wise proof. Okay, so the thing is, trace of outer product of two quantum state psi1 and psi2. Now I am taking a different thing. I remove the operator here. Okay. Just simply trace of outer product of two different quantum state is same as the inner product of the quantum states. So this is the property. Trace of outer product is the inner product of quantum state. Okay. These are the basics, sir. So I mean, I could prepare slides and I could show you all the applications, right? These are the applications of quantum information theory, insecurity, many other pillars and all. But at the end of the day, probably it won't help you much, because I thought, like, let's use these 2 hours to understand the basics, because at some point of time you will explore research papers, you will explore many other things, people will talk many great things, and you will then try to connect. Okay, sometimes back I at least have the understanding what the density matrix is. Now I can read a paper. At least even I can't do research, but I can at least understand what a paper tells about, right? So that's why I'm just trying to make use of these basic things. Yeah. Is the order of psi1 and psi2 matters in this equation? Okay, good question. I haven't thought this question. So, in general, for matrix multiplication, if a matrix is m cross n, then to multiply another matrix has to be n cross p. At least these number of rows should equivalent to number of column. Now, to vector outer product, similarly, there has to be, because psi 1, if I consider, it's an because it's a column vector, right? It's a column vector. So if it is n cross 1, then the psi2 can be basically 1 cross anything, 1 cross p. So effectively it will be some n cross p matrix, right? So mathematically there is no harm, but in general, when we talk about the quantum computing principle and all, we prefer the square matrix, and in fact physicists prefer the Hermitian square matrix, okay, because they have some beautiful properties. So I'm not covering those aspects, because maybe in future if I take some algebra classes, so I'll cover some of those aspects. But you are, in general this is correct, but for quantum computing there are some more constants. Okay. Same question. What is the meaning of completeness? Rule. Okay, nice. Okay, in the material I have given what the completeness means and all. Okay. Okay. Maybe some portion I can try here. Just I have another 1 hour. Okay, just let me give the proof of this, and then I'll go to another topic and I'll cover some of this completeness and other relations. Maybe okay, because I have to cover the decoherence parts as well. Completeness is an easier one, not a difficult thing. It's same as the probability rule. Okay. Okay, so let's give a 2-line proof for this. So trace of psi2, psi1, or psi1, psi2, same thing. Is basically, we can write the definition in this way: sum over I, psi2, get I, psi1, which is same as sum over I, psi1, psi2, I, which is same as psi2 outer product, and this psi2 is coming outside, and this over I, get I times get I, and then another vector psi1. This is just the way trace is defined, and just interchanging some of the elements which are independent of I. Just we are giving it outside, and this is the inside part. So so I is some computational basis, right? So then basically outer product of all the computational basis will be equals to identity matrix, right? For all I, and then it will be your psi2 and psi1. This is the proof, generic proof. Now this step is crucial. This is identity matrix, right? So what I mean, like, in when you do orthogonalization of matrices, right? So for example, let's take an example. Suppose you do A is some matrix and you do some QR factorization. Okay. So all these basically columns of this Q matrix, like this one, like this, all these columns, right? They are orthonormal to each other. Like if you do the inner product of between two vectors, they will give 0, right? So they are orthonormal. Similarly, when you have done the basically the echelon form of the matrix A, and then basically you have done the Gauss-Jordan elimination process and all, you have seen that you can do something, and the left side it can be some E1 vector, E2 vector as the orthonormal basis, right? And so on, where E1 is basically equals to your 1 all 0. E2 can be your 0 0 0 all 0, then 0 1 all 0, and so on, these kind of matrices. Okay, so that means if you take the individual vector as E1 and E2, the second vector and all, and if you do multiplications, right? So basically if you take the inner product of E, so like E1 times E1, right? The product actually it will be control J. So sorry. So if you do these things, like then E2 times, this is just simple linear algebra and so on. So you'll find the sum will be actually equals to additive matrix. Means this matrix is entirely equals to 1 1 1 1 1 all 0. So altogether, if you do the outer product and sum, okay, property is used here, like here. So it's additive matrix, then psi 2 times psi 1. Okay, so it's fine. Like this is simple algebra, and then let's go a little bit more about some more metrics, um, in quantum information theory. So I'll just quickly cover this part and give some notion of quantum communication channel, noisy communication channel, and decoherence just after this. So let's quickly cover this part. Okay, there is something called fidelity. So there are two types of definitions of fidelity for pure state and impure state with density matrix as well as the vector definitions. So suppose what we do, suppose there is a quantum state phi and there is another quantum state psi. Okay. Now you might be interested that what is the similarity of these two states. Why I'm saying so? Because suppose hypothetically assume that there is a transmitter. Yesterday we were talking about this, right? And you generate some signal ket psi, ket phi, suppose. Okay, this is your input signal, and there is suppose some quantum communication channel, and there is a receiver Rx, and whatever you have received is some ket psi. Okay, or simply suppose X is transmitted, Y is received. Okay. Now you might be interested whether I have received the same signal or not. It's the same signal or something has happened in between, right? So then basically what we do these things. We do the dot product between these two states, X and Y, okay, and take the square. So this is called the pure state fidelity. And there is a circuit for this. We normally do the swap test circuit. Swap test circuit for computing the fidelity of quantum states like correlation and all. So in general, what happened is that from Schrodinger equation, like if we consider it's an isolated system, that it is not interacting with anything else, then we know that okay, um, so basically h bar del t of my wave function is, the equation says it is the Hamiltonian times the wave function. This Hamiltonian might have a kinetic energy and energy part in general for the physical phenomena like fermionic and other things. And if you solve this equation, what you are getting that your evolved state is basically your initial state times e to the power minus iht, right? So this is the solution of your Schrodinger equation. And this e to the power minus iht, you can check because h is some matrix now. And if you can say that e to the power iht times e to the power plus iht is basically some identity matrix, right? So basically it's an unitary matrix. So unitary matrix, and we know that u star u is actually identity, or u star equals to identity. But together you can always write u star equals to u inverse, right? For the unitary matrices. Now, this equation is saying that if there is a time evolving process, okay, that some quantum information is passing from one point to other point, that means there is a time evolution for that delta t amount of time, delta t, but delta t may be your t2 minus t1 within that time, times the initial wave function psi1, psi0, right? And in this example, here it is ket y is equivalent to your psi evolved state, and this is your equivalent to your psi initial state, ket 0. So basically, what we are getting effectively ket y equals to some u times ket x. So our basic quantum communication model becomes. So nowadays, what communication people are saying in terms of security, I'm not going to that aspect, QKD and other thing. That is a separate ball game. Okay. So I am telling the simple mathematical part or the information theoretic part of the communication. Okay. So where you transmit some data X, it goes through some system U, and you are getting some Y. Simple engineering. You have some input to a system. The system is A. It may be some LTI system or control system, and you are getting some Y. Here you are giving the input Ktex. It is evolving through some channel U. This is called channel. Now, earlier in computing, these were simple quantum gates, right? Now here it is called quantum channel because this may belongs to place A, this may belongs to place B. They might not be in the same place, and you have designed some noiseless channel U such that you get Y, and Y is actually equals to U times Ktex, right? Now the question is, if it is pure, right? If it is pure, if there is no loss, if no loss of information, no loss of information, then our outer product is our fidelity is. So we have defined fidelity as inner product of y and x, right? Y and x, that is phi and psi, right? Here it is y and x, right? So here y is actually your n square, right? So here y is basically u ktex, right? And x is already ktex, right? So this is what you are getting, right? So ktex times ktex is what? So basically, this is basically u star u, right? That is equals to identity, because we already know if x is some quantum state, some, because it's a unit vector, basically some unit vector. So basically x star x equals to 1, right? So also you can do this kind of proof as well, like if you have some x, right, and if you multiply u just this way, so this is same as basically ux star ux, that means x star u star ux, that means x star x, right? And because you are taking the square of this, so you are getting some. So basically, if there is no loss of information, you are getting some same fidelity, right? So what was transmitted exactly that you have received, right? But the case is when actually ktex is passing through some channel u, and you are getting some y, that you may interact with the environment. And from this point, like now you have two systems. One is your actual system and one is your environment, right? Now there is an interaction between your quantum actual hardware with the, it may be photonic, it may be something else, it may be superconducting, it may be ion trap, it may be something else. But your qubit is interacting with the environment. That means there is a composite evolution, right? And this entire physics is called the open quantum system. So we started with isolated quantum system. Now it becomes open quantum system. And your Schrodinger equation is no more valid here. So in general, we think this way. So there is a separate kind of equations and evolution and all. So like the master equation and all other things are there, but I'm not going to that direction. But in general, this U can be a pure state pure U. It can be a noisy U. Okay. So that's why fidelity is extremely an important quantity. Okay. And let's take some example and do it. Okay. So that you don't feel sleepy, because it's the like just after the lunch we started the session. So let's do some exercise. So some ket size, suppose 10. Okay, sorry. Suppose it is 10, and suppose you have some phi at 1 by square root 2 1 1. So somebody let me know what is the fidelity. Calculate the fidelity and let me know the answer. Yes, correct. The answer will be 0.5. So just you apply the formula and you'll be getting it. Just it's simply like 1 0 outer product with 1 1, and you take the square of this. So it is equals to 0.5. Okay. And there is a density matrix definition of the fidelity. Okay. So this is like the pure state definition. And another definition is the density matrix definition. Density matrix definition. So now the fidelity between two quantum state rho and sigma. So where rho and sigma are two density matrices. Okay. So what is the similarity between the density matrices of two quantum state? Because at the generation of ktex, now there might be uncertainty. There might be many such ensembles of ktex1, ktex2, and so on at the input side. So this may refers to some rho. And at the receiver, you do multiple experiment and you get some y1, y2, and so on. You get some, sorry, you get some yn, and this is some sigma, right? Yes, yes. So now we have to compute the density matrix definition, that is f rho sigma, which is equals to trace of square root rho sigma square root rho and square. Okay. So let's take an example. Suppose rho equals to 1 0 0 0, sigma equals to half of 1 1 1 1, and calculate the fidelity. Rho equals to. So let me know what is the answer for this. So here you can see square root rho equals to actually rho. I have given an example where you do not need to compute square root. Okay. So solve this problem and let me know the answer. Then I'll go to the decoherence and little bit more on the quantum channel side. Anyone? Please check the answer. It is not one. Yes, it is 0.5, correct. So thank you. Now, little bit, let us talk little bit more on the channel, and then I'll go for various uncertainty, especially the decoherence part and the noise part. Okay, one more definitions let me give you. So that is so we have seen that if it is a pure like evolution, pure state evolution, we have seen that the evolution is given like for example x t plus 1 as so this is just simple definition. You just need to put all the things, is simple matrix multiplication things. So most of the answers that I'm seeing in the chat box are correct actually. It's not that difficult. Okay, in the text material, the solution is given. So the text material will be shared with you. So we have seen that the pure state evolution is given by xt plus 1 at time t plus 1 is at time t and this way, right? And then basically let us define some evolution in the density matrix way, where our density matrix is suppose rho times rho. Okay, and suppose our evolved time equation is a rho prime that we define, that is basically rho prime is what? Rho prime is basically okay, so I'm so sorry, just let me change the notation. Psi t plus 1 and psi t, and suppose this is your psi t plus 1, these are psi t plus 1 outer product with psi t plus 1. Suppose this is the outer product density matrix at the evolved state, then you can always write it as the first state is basically u times psi, right? And the second state is psi times u dagger. Any problem? Like, so this particular you can write u psi, and this you can write as bra u dagger, right? Same thing, like it's a bra notation. So this is u rho u dagger. So this is critically important equation for time evolution. This is same. This is Schrodinger equation, solution of the Schrodinger equation for density matrices. This is noiseless case. Okay, so this is an important equation for the noiseless case. And typically, if you have environmental impact, although I'm not covering much of this because this is okay. Most of slide. Please allow me a couple of maybe seconds, so just to have more slides. Yeah. So, okay. Yeah, so I'm not presenting the Heisenberg representation. So, yeah. So there are two different pictures, Schrodinger and Heisenberg thing. Maybe somebody from the physics background will explain much better than me. I'm skipping this question. Okay. But definitely like the evolution, whether you are representing in terms of operator or in terms of the like quantum state, that's a different way of representing the time evolution. So just skipping that part. Okay. Now, um, now suppose there is environment is playing. That means you have a just 1 minute. Suppose now your this is your quantum system A to B. There is some channel, quantum channel, but environment is acting here E, right, with your system, right? So then basically what we are doing is, so we are interested about the system, not in the environment, but the composite evolution can be something like rho system will be equals to U system evolution of rho s, the system evolution tensor product with the if we initialize the environment at 0 e, right, 0 and u dagger is c. So the equation can be more complicated. This is just one of the thing, and we normally take the partial trace over it to remove the impact of the environment and to get the system back. So so I'm just not going to these directions where basically your system will interact with the environment, and basically your system has an evolution US or USE, and then basically you have another evolution for like interacting part with the environment. So there will be a composite evolution for this entire system, and you have an initial state, right? So this is the like this is a different topic. Maybe in QT-06 or some other QT it will be covered. So I'm skipping this part. Maybe we can go to the other important aspect like the Krauss operator definition. So because that is in the syllabus, at least I should define this. So this Krauss operator actually is important in to deal two things. One is the quantum channel part, and the that may be the so noisy or the noiseless. Mostly noisy case, this kind of operator are extremely helpful, and so they are basically the definition will not be clear today because it will take at least couple of classes to understand. But let me define. So so the most general representation of a quantum channel E, that is completely positive, as well as the trace preserving and trace preserving, which is together known as the CPTP map, and for those kind of quantum channel, the Krauss operator defined as the um, E of the density matrix rho as sum over k ek rho ek dagger, okay, where sum over ek dagger is same thing like the computational basis for the pure state, right? Not for the density matrix, equals to identity for all k, and this is basically the completeness relationship for this Krauss operator. Completeness relation for the Krauss operator part. Okay, so where EK correspond to possible interactions between the system and the environment, and this representation allows the efficiently model a wide variety of noise process such as bit flip, phase flip, amplitude damping, and depolarization channel. So, for example, let us instead of going much detail about Krauss operator, let us understand this part with some examples. So, let us take some example from the some channel. How much time I left? Okay, I have roughly 25 minutes. So let me define some of the things. So channel as an operator. Okay. So what happens is that when information pass through a channel, right? We suppose we get X and suppose there is a channel in between. Okay. So there are a lot of things happens because quantum information, these are the complex quantities that we are basically treating here. And so this is not only about the information are just not only kate 0, 0, 0, say kate 0, 0, 0 to some kate 1, 1, 1, but also the associated phase. So both the phase information we have because they are complex numbers. So basically there are several quantum gates that is associated with these qubits, right? They carries the phase information as well as you have the bit information, right? Bit information you have. Those kind of both kind of information are there, but there are physical hardware, right? So if you are working on the superconducting qubit, so maybe you can have some phase gate or you can have some combinations of CZ gate or CX gate, right? Also other gates. So when you are actually applying this kind of gates to a qubit, say for example, you are applying some 0, 0 state to with a CX gate, right? CX gate just we have defined. Now, this is fine. Mathematically, they are fine. But what actually is generating this CX gate? What is the physical hardware that is responding to this particular CX gate, right? So that particular thing, actually that particular generation might actually face different kind of errors, like especially two kind of problem we'll see. One is the decoherence. I mean the time constants T1 and T2 related to like how much energy dissipate they do and the other thing, right? So there are decay equation. I'll roughly cover a bit on this later. Another part is the noise, physical noise. So there are several kind of noise, how it looks like. So maybe before leaving the class, I'll show you the real hardware picture. What are the different kind of decoherence and noise on a real hardware? Similarly, sorry. So similarly, if there are those who works with the photonic quantum computer, right? So I visited some of the labs at IIT Delhi and some places. I have seen that they try to keep the room as dark as possible because if light, normal light or tube light or other light, they interact with your quantum information. In fact, so there also you have an different kind of errors, right? Because suppose in a device you are trying to pass the information from A place to B place in a in a photonic quantum computer with beam splitter and other different ledger and other scheme, other hardware scheme. But if it is interacting with the environment, so there is a high chance of losing information, both the phase and the bit information of thing. Similarly, in the superconducting chip, when you are actually applying the different kind of gates like phase gate, CX gate, and different kind of gates, especially the 2 qubit gates are more noisy, like CX and all. CX means Cnot gate and all. These are more noisy. Single qubit gate, they are mostly rotation gates and they are fine. Like their coherence time is good and they do not as such do the error. Okay. So, but in general, there are errors and let us understand some of the errors. One is called the bit flip error. So in normal digital communication, what happens? So suppose you transmit 0, but you receive 1. So there is an error, right? So suppose you transmitted 000, but you received 001. So 1 bit of error information is there at the receiver, right? And there are several metric or the quality of service parameter, okay, which actually quantify how much error is there, like BR performance and other things. Similarly, in quantum also, like some of the tools like Fidelity and other things I defined, and there are other tools as well. So here, suppose your information is 00 kate 00, but suppose you received actually at the receiver or at somewhere where you are doing you are measuring your result. So you suppose your quantum state is kate 01. That means there is a bit flip. 0 has become 1. Now, what makes this bit flip? Right? What does actually make this bit flip? So it's like a Pauli X gate. Pauli X gate, right? And the Pauli X get the definition X is basically 0, 1, 1, 0, right? So if you apply X to the 0, you will get 1, right? So this is basically matrix time per vector 1, 0 times the 1 0, you'll be getting 0 1, right? So this is what you are typically getting. That means poly X gate here is acting as a noisy quantum channel. Noisy quantum channel. Quantum channel. So noisy quantum channel that is basically doing the bit flip. Now, why you can think, okay, this is trivial. Everybody knows about this, of course. So suppose you transmitted some long bit stream 0 0 0 0 0 1 0 0 0 0 1 1 1. Okay, and suppose you received something, some bit stream 0 0 1 0 0 1 0 0 1, something like this. Okay. Now, definitely from the fidelity checking and other things, you are pretty much sure that I haven't received the correct information. But how to model that what information I got, what kind of errors had happened in between, which changed my bit informations, right? So you can model that there is some noisy evolution, okay? And probably the noisy evolution is the tensor product of some polygon. This is not the obvious model. This is not the obvious model, but this is some model, okay, which may help you to model your output information to the input information. Now you can design a quantum circuit, right? How to mitigate this information such that you get as close as possible to your transmitted data KTX, right? Suppose you transmit KTX, you receive KTY, but you are pretty much now you are confident, okay, there is some UX working, U noisy working. Now, if I can design some UX star such that this intermediate noise is eliminated, and I get some perfect, almost perfect KY, which is the fidelity of Y tilde and X tilde is nearly 1. So these are the techniques called the error mitigation techniques. Um, error mitigation techniques. Sorry. Error mitigation techniques. So there are lots of methods I am not covering today. So whenever you get some information, how to model them, how to remove the error and all from your circuit. So this is one way of thinking. Now the next part, okay. And now the next part is now suppose at the output, when you should not use this model, that is also we should know. So perhaps this kind of mitigation is possible when the error type is consistent. Maybe you're correct, sir. So I'm just covering some basic things here. So for highly random noises, there are like advanced techniques like probability error corrections and other things. So PC, JDN is one of the basic things. So I'm not covering the error mitigation techniques today, but yeah, you're correct actually. Yeah. So but if you apply the X gate to the plus basis, plus X, so this is a superposition state, right? And your basically you're applying X to the state 1 upon square root 2 1 1, right? This is your superposition state 1 1, right? And so simply understand this. Let's remove this complicated equation. So suppose X you are applying to plus state. So basically this is your 0 1 1 0. So I must have the eraser with me. Okay, so basically your plus state is what? Your plus state is 0 plus 1, right? Because you have applied the Hadamard or something. Then suppose your square root 2 is outside. Then basically if you apply X, so your 1 become 1, 0 will become 1, state 1, and 1 will become the 0 state. But ultimately you are in the same state. Again, it's a plus state, right? So you are applying some superposition state on the and you are applying the poly X gate to some superposition state plus, but you are getting plus back, right? This is same as Ax equals to lambda X equation, right? Eigen equation. So with eigenvalue equals to 1. So superposition state is an eigenbasis, right? Is an eigenbasis of Pauli X gate. So basically, what it means visually, let's look at this. Suppose this is your Bloch sphere, right? And this is your superposition plane, right? This is gate 0, this is gate 1, right? And this is your plus gate, and this is your minus gate, right? So even if you check, if you apply minus with this, like x minus, you'll be getting minus of minus probably. Check it, okay? So where eigenvalue equals to -1, and this is the eigenvector, okay? So as soon as you are here, hit psi, right? You can do, if you apply the x gate, there will be some rotation, 90-degree rotation, right, along the x-axis. And suppose if you are in the gate state 0, and if you apply, suppose this is your vector, and if you apply the x gate here, your state will come here, gate 1. But if you are on the eigenbasis, and if you apply x gate, it won't do anything. So if your state is like this, plus state, and if you apply x gate on it, x on plus, so it won't change the direction of x, and it also won't change the amplitude of x. So that's why plus state is the eigenbasis of x. So if you have an outcome state psi at the receiver, and there might be lots of gates, right? Lots of time evolution where you have done superposition, you have done interference, entanglement, many other things, and you try to design a noise error mitigation circuit with only x. It won't work to capture how much amount of variation is there with the superposition state with only simple x gate, right? So that is like you can visually clarify from here. Okay, so now take another gate, that is the phase flip gate. Now let's take the Pauli jet matrix. Okay, so Pauli jet matrix, the definition of Pauli jet is 1 0 0 -1, right? This is the definition of your Pauli jet. And what it does is that if you apply jet to the computational basis 0, you'll be getting 0 back. Let's prove it. So 1 0 0 -1, and it is basically 1 0. If you simply multiply this matrix times the vector, you'll be getting 1 0. And if you do g times, sorry, it should be gate 1, you'll be getting so basically 1 0 0 -1, it will be 1 0, and it will be your minus of gate 1, right? So this is also following the eigenequation x equals to lambda x, where lambda equals to 1 in this case, and lambda equals to -1 in this case, right? So what is happening here? So you can see that so if there is a bit, there is a 0 bit, and you apply a G gate here, right? So there is no change. But if there is a 1 bit and G is there, so there is a minus sign coming in front of 1. So this is impacting the phase impact. So if your answer is getting like lots of phase variations and all, you can model them, try to model them using the Pauli G gate bit string, and if you see like the superposition state now, plus state, and if you apply the G gate here, right? So you apply the G on top of the 1 by square root 2, 0 plus 1 state, right? So what the Z gate will do, 1 by square root 2 will come outside. So 0 will be 0 and 1 will be -1, right? So it is your minus state. So you are applying G gate. So superposition state is becoming the opposite, minus. And if you apply, so basically plus is becoming the minus, right? So this is also a NOT gate now. So maybe in quantum computing when you started, right? So people have told you that X is called NOT gate. It's called a NOT gate. But this is called a NOT gate for computational basis. Okay. Z gate is also a NOT gate for superposition basis or Hadamard basis. Fine. Barsha Sambhaji. So what is your question? It's not clear. The last question. Can you please explain your question more? I'll quickly cover the decoherence part for 5 minutes, and then I'll show you what how it actually impacts the real physical hardware. Okay, fine. So I'm not getting any question as such. Oh, that it's on notice. Okay, fine. Okay, so decoherence is probably one of the very critical, I'm saying critical phenomena for practical quantum computers. All practical, not theoretical, all practical quantum computers. So the central challenge in quantum information processing is maintaining the delicate quantum states that enable phenomena such as superposition, entanglement, and all. So because quantum systems are inherently fragile, even slight interactions with the environment can disrupt their coherent behavior. And that leads to errors in computation and communications. Okay. So among various disruptions, so basically there are two types of things. One is the decoherence and another thing is noise. Okay. So decoherence, basically, suppose you have a qubit and suppose it is holding the superposition state plus state, right? So that means it is a superposition between your 0 and 1. But how long it actually hold this state, right? It cannot hold it for infinite time because it start interacting. So we cannot create a temperature like absolute zero. We cannot create a total ideal environment where qubit will process the information infinity time for superposition state or the entangled state. That is never a possibility. In reality, every quantum information try to decohere. That means they try to basically try to collapse the state, right? So that particular phenomena is called the decoherence. Decoherence refers to the loss of quantum information, quantum coherence, due to the interactions of the quantum system with the surrounding environment. And so there are things like several time constant. One is called the relaxation time T1. Relaxation time T1. And another particular constant is there that is called the dephasing time. Dephasing time T2. So these time constant are extremely important. How much better are they? And accordingly, your qubit will act like, I mean, suppose you are designing an algorithm to solve a problem. Suppose you have a problem like finding the spectral component of a signal. Suppose x gate x is a signal, and you want to just see the spectral component of the signal in gate y by applying the quantum Fourier transform, right? It's great because everybody will say, okay, quantum Fourier transform has some better gate complexity advantage or anything. It's a good algorithm. Fine, no problem is there. But QFT contains some number of n number of gates, n number of say 2 qubit gates, and n2 number of N2 number of single qubit gate. Okay, single qubit gate, single qubit gate. Now, single qubit gate which is acting on only single qubit. Suppose this is some rotation gate. Okay, fine, no issue. It may have a better relaxation time, better dephasing time. But there might be an entangle gate in the second qubit to first qubit. Maybe there is some Cnot gate, right? Or swap gate or something like that, which basically is performing the QFT algorithm. Okay, but this particular gate might have a poor T1 and T2 time, right? So that means so when basically you increase the number of qubit n, suppose n equals to some 10 qubits, then this circuit will be huge. Like this circuit will be huge, like Ket0 to all to up to 10th Ket0, right? And there will be lots of single qubit and lots of 2 qubit gates. For them, every individual quantum gates actually is taking some time, T1 and T2. Okay, and together you will see that there is a lot of loss of information. Then you are supposed to get some peaks like this, your frequency peaks F1 and F2, but actually you will be getting a lots of peaks which are not important, which are error actually. Okay, so that's coming because of the decoherence. Okay, the question is why always KTX is used instead of BRAX? Okay, sir, you can use BRAX, no problem, but okay, I can take this question some in future, like why we prefer column vectors, right? The question why we are using the column vectors. Row vector you can always use, but I'll suggest you, sir, to go to the lecture series by Professor Gilbert Strang. Gilbert Strang on YouTube or MIT OCW to appreciate row picture versus the column picture. Row picture versus the column picture. And you will see that our brain works better with column picture, but we visualize less with the row picture. Okay, so a better answer given by Professor Gilbert Strang MIT. I'll suggest you to go to that particular lecture. Okay, I am not covering that here. So before, I mean, there are a lot of theories of decoherence and other things, but I mean, I'm not going to detail of this because this is already given in the notes. Better, I'll show you. I'm stopping here to take some question, and as well as I'll show you what the reality in, because I'm from the industry, so I should show you some reality in the practical product. Just I'm just de-sharing my screen and then I'll come again. So maybe in the meanwhile, so Professor Ashish is here, sir. You can take some questions or anything, and I'll just simply share the error part with IBM quantum system so that people get a flavor how the error works.
Yeah, sure, sir. Hello, am I audible, sir?
Yes, yes. So I'm just sharing my screen once more.
Yeah.
Is it visible, sir?
Yes, sir.
Yes, yes, just okay. Okay, so so if you go to ibm.quantum, like quantum.ibm.com, our official website where you can access the quantum computer, you'll see that you can create any account, like free account or anything, like to just get a flavor of real quantum computer. So what you'll see that you check with some machine, like let's take a quantum computer from here. Say Brisbane, IBM Brisbane is a hardware, and you see there are lots of things are there. There are 127 qubits which are actually designed like in the hardware in this heavy hexagonal kind of lattice structure, and 2 qubit errors that each 2 qubit like CX, CZ, they have a best performance of 3.21 time 10 to the power minus 3. This is the error rate. Layered, every layer wise, this is the particular gate error. Okay, what are the basis gates used here? Means whatever circuit you design, uh, then basically you try to convert the problem to ECR, ID, RZ, SX, and X gate, poly X gate. Okay, so these are some of the gates might be. What is the median SX error is 10 to the power minus 4 and all. So basically, you can expand the map, you can see these things. Each individual qubit has a particular error. You see, if you click any of the qubit, it has, there are multiple types of error, readout error. Okay, so and as well as the I should show the time, right? T1 and T2 time. See, there is a median T1 time and T2 time. These are responsible for your decoherence part. So US means it's microsecond. So 230 microsecond and 130 microsecond. So basically this much basically are the time constant T1, T2, and from there you can calculate what is the coherence time and decoherence time for your particular machine. Okay, so we should not take much time to solve a particular problem. So our algorithm should be optimally designed such that total time taken by the quantum computer is justifying the coherence time of the qubits, so that you get a perfect result. Okay. These are also readout error performance, some tables. Okay, this is nice one. So these are the T1, T2 decoherence time constant T1, T2, and there are other particular qubit to qubit readout, assignment error, probability of measurement error, readout error, ID error. So there are different kind of gate level error. Suppose you are using some Pauli X gate. So what is the error level? What is the ECR error level of a particular gate? What is the time taken by a particular gate, like in nanosecond and all, if you interact with qubit 1 to qubit 2 by some 2 qubit gate and all. So there are different kind of real error performance is there. So when you design some algorithm, please consider this kind of error performance to improvise your algorithm for practical purposes. Thanks a lot. Like, this is all about the quantum information science. It is it's a big subject, and my understanding is much less. I don't know much about the subject. Just from my practical experience, I just tried to capture some of the probability theoretic things, and maybe in future, if I get an opportunity, I'll try to take some more session. Thank you so much.
Yeah. So thank you so much, Raman sir, for this a much complicated concept in computing in a very simple and lucid way that you have explained. Yes, of course, these concepts are not very straightforward to be grasped, but still the way of explanation is quite nice here. I hope that all the participants will be in a sync with whatever the content that is being delivered. So thank you so much, sir.
Yeah, thank you.
First for joining us and giving such this quite insightful information about the topics.
Right.
And I think it's already 4, and most of the questions I think you have already
Yeah, I shared the
yeah,
material for yesterday and today's class, as well as some MCQs that is might be required for your evaluation. Questions
yeah,
are
right,
pretty
sir.
much very easy kind of thing, and I asked Pilli sir to give more and more marks to everyone. Yeah,
Yeah,
thanks.
sure, sir. So we will do that. And whatever the material that you have provided, it will be uploaded by today itself.
Sure.
So
Thank
not
you,
an
sir.
issue. So thank you so much, sir. Thank you so much for joining. And I think thank you so much, sir. Thank you.
Bye.
And there is one announcement for the participants as well, that we have also extended the quiz one